It's my pleasure today to talk to you about a couple of new things in perimetry, specifically CEDA Faster and 24-2C. We've had the perimeter, the Humphrey Field Analyzer, with us since 1984 in a couple of iterations. And in 2015, the Humphrey Field Analyzer 3 was launched. And there's been some significant updates just very recently. And in particular, I'm going to talk to you about CEDA Faster, specifically CEDA Faster 24-2, because it's not available in the 30-2, and also CEDA Faster 24-2C. And also the fact that with these new programs, we can actually, in our guided progression analysis, we can mix all the various different CEDA protocols to ensure that we can use our old information, our old clinical information, along with these new programs, and that's obviously very important. So CEDA Faster tests the 24-2 in usually around 2 minutes or less. It's 50% faster than CEDA Standard and around 30% faster than CEDA Fast. Clinically, it's pretty much equivalent to CEDA Fast. It's basically based upon the same CEDA algorithm and uses the same normative data as CEDA Fast. But there's various tweaks that were made to CEDA Fast to make it faster. In the original CEDA Fast and CEDA Standard, there was much longer breaks between stimulus presentations that are taken out of the CEDA Faster. Also, that there's no blind spot check and there's no check of false negatives. False positives are used still as a quality monitoring catch trial, and gaze monitoring is used to check through fixation. There's been a major publication that outlines these changes, a multi-center study that looked at CEDA Faster versus CEDA Fast and CEDA Standard. The title's A New CEDA Parametric Threshold Testing Algorithm, its construction, and a multi-center clinical trial. So this was just released, and the purpose of this study was stated as to describe a new time-saving threshold visual field testing strategy, which is intended to replace CEDA Fast and to report on the clinical evaluation of the new strategy. So we can see from the first table from that paper that there's a significant difference, as we might expect, between the test times, and also a little bit of difference on the VFI. Other than that, most things were pretty similar. Test duration here, you can see the distribution of test times across all of the participants in the study. And we see consistently down at the bottom there in the blue squares, CEDA Faster being the quickest algorithm. Somewhat of a comfort, you can also see that each of the tests classifies the visual fields in a similar way, gives a similar level of defect, and certainly is really no different than the sort of performance that we see if we were comparing CEDA Standard to CEDA Standard or CEDA Fast to CEDA Fast. The conclusion of the paper is that CEDA Faster saved considerable test time. CEDA Faster and CEDA Fast gave almost identical results. And there were small differences between CEDA Faster and CEDA Standard, but of the same sort of magnitude and the same character as between CEDA Fast and CEDA Standard. So CEDA Faster really does genuinely seem to be give us very, very similar results. The only thing that you'll find a slight difference is sometimes an increase in the number of false positives that we see, and that's really just given with the speed of the test, that with some patients you get a few more false positives. The really great thing going forward is that we can use the CEDA Faster results in our guided progression analysis, and we can see here an example of using a mixture of CEDA Standard, CEDA Fast, and CEDA Faster, and still being able to mix for both the baseline and for looking at our both trend and event analysis. As we see in this particular case, the additional macular defects showing up on the CEDAR FASTER final data set at the bottom of the field compared to the two baseline results at the top. I'm just going to show you a quick case here. We've got a 54-year-old Korean woman, normal tensions, 15 and 14, corneal thickness normal, gonioscopy normal, but we can see very dramatic notching of the rim and a nerve fiber layer defect. No surprise that that's confirmed with the inferior defect shown on the nerve fiber layer analysis here. Here we can see a defect really threatening fixation. And this, of course, is the sort of presentation where we've always been encouraged to look at the 10-2. And here you can see the 10-2 in this particular patient. See really just how serious the defects are here in spite of the patient's young age and relatively early presentation. But we can see these really worrisome defects threatening fixation on this 10-2. And of course, one of the problems is we've never been able to really follow progression in 10-2. We don't have the analysis in order to really monitor change in the 10-2. We can just measure the field. And just a reminder of where on the visual field these test patterns cover. You can see in the blue here the 24-2, covering over that central 25-degree area of the visual field. And we can see in the red dots there the 10-2. And there's very few, there's really just really 4 points that overlap between both the 10-2 and the 24-2. So when we measure the 24-2, we really are not looking at very closely or very carefully at the macular region. Growing evidence has suggested that some of the defects we see in the nerve fiber layer that we're not seeing defect in our 24-2 with our 6-degree grid can be found if we measure with a 10-2 and really look at that macular area in greater detail. Because of that and this growing need that was identified to try and really measure macular points a little more carefully, there was an expert group put together to look at what evidence existed in terms of where we should place locations if we wanted to get extra information by combining additional macular testing with a traditional 24-2. And here you see that the test locations that we eventually ran with are shown in the red boxes. And so after quite a bit of time following this expert group meeting, there was modeling and additional work to really look at the ability of these points to detect the early nerve fiber layer defects that we sometimes see. And these are the 10 points that were selected. The evidence suggested some points were just slightly off from 10-2 points, but they were always very close. So again, a strategic decision was made to align the points that gave us the most information with 10-2 points so that we could make sense and have the data available that would link in between this test and the 10-2. So on this particular image, you're seeing the large gray dots of the 24-2 pattern, the large orange dots are the 10 additional locations from the 24-2C, C standing for central, and the small dots, the small gray dots being the traditional 10-2 pattern. And there's not a lot of publications yet about the 24-2C, but there was a poster presented at ARVO just a year ago that looked at the ability of the 24-2C to measure some of these locations. And we'll certainly be looking at some cases shortly that will really identify or illustrate how well the 24-2C can work in some cases. And here we see an example, a right eye on the left, the 24-2 CEDAR FAST, and within normal limits in terms of the glaucoma hemifield test, and no real obvious visual field defect. But with the 24-2C, and certainly see that there are several clusters of points that we'd be more concerned about that may match with the macular defects. So the 24-2C is there to, or faster is there to minimize time. The 24-2C is to minimize time with CETA faster, but maximize information and give us more information from the macular region. So the 24-2 CETA faster saves us about 30% from CETA fast. The 24-2C is about 20% faster than normal CETA fast 24-2. The 24-2C is not available for CETA standard, and really the idea behind that, or for CETA fast for that matter, but the idea is that we're really planning to standardize going forward with CETA faster. And this is really because of evidence base showing that even if CETA fast was perhaps a little more variable on a single visual field, over time and looking at progression, it's no worse than CETA standard. So the idea of measuring more fields with the time you have being better for this idea of looking at progression. So it's being standardized that CETA faster is just on the 24-2 and just the 24-2C is only available with CETA faster. I wanted to finish off just putting a slightly different twist and looking at some structure function. This is an amazing paper that was published a few years ago in IOVS that did some fairly high resolution mapping with OCT and then looked at the visual field, 24-2 visual field, and looked at predicting what the visual field might look like purely from the OCT data. So here on the right-hand side, looking at the top, the early glaucoma, then moderate in the middle, advanced glaucoma at the bottom. This is the group average of the participants in each of those groups. And what we see is the average measured visual field on the right side. And in the middle there, you'll see the predicted visual field. You can see how close the match is by predicting the visual field simply from structure. And if we look here, we can see a remarkable set of raw data, far too much information on the slide really, but if you pick up any one of those pairs, whether it be in early, moderate, or late, in each of those pairs, the field on the right-hand side is the measured field. The field on the left-hand side is predicted from imaging, predicted from OCT. I know there's a few times where there's mismatches. I think you can see most of the time. It's really quite remarkable how similar the visual field that's predicted from OCT compares to the measured field. So where's this leading us? What am I getting at here? Well, one of the problems with our guided progression analysis is needing good baseline, needing good data, and more data to get us going with our visual field. So if we could add in predicted data from structure, from our OCT measure, how might that save us time, for example? So we know that if we have a prior field, if we know what we think the visual field looks like, we can save 20 to 30% on our test time by using that data in an intelligent way to seed and predict where we might be with our measured visual field. So it just this idea of using structure to predict function and get us started down the road to a quicker visual field testing. So I think we'll see some really exciting developments in this sort of area of perimetry and visual fields. I think also we may well start seeing mixtures of target sizes, perhaps bigger target sizes that give less noise and less noise measurement error in our patient measurements and may allow us to, again, see progression a little sooner if we're measuring with bigger targets that give us less noise and a greater range of measurement. So I think we've got some exciting times ahead. Available now to you is CETA faster. and the CEDAR Faster 24-2C, both, I think, significant contributions towards our clinical care of our glaucoma patients. So next we're going to look at some cases together with Dr. Murray Fingerette, and I hope you enjoy the idea of measuring our fields faster and with more information in the macula.